Martingale theory, okay, and Girsanov theorem as well. So what would be the expectation of e to the this stochastic integral 0 to t h of s dws? Can I compute it? Yes, why not? It's just a normally distributed random variable. Okay. So the expectation of this is going to be, okay, so you need to integrate, say for example, from minus infinity to infinity. I'm not getting into the whole computations, I'm just mentioning it and leaving it. So I want to integrate this guy. So e to the x, and by x I mean this, times the PDF of this guy. And what would be the PDF of this guy? The PDF of this guy would be, okay, so e to the minus x square over 2 times of e to the 2 sigma square actually, and the sigma in this case is this h2 norm. Okay, h2 norm is square. Okay. And dx. Okay? My claim is that you can solve this integral. So what you need to do? So you need to add this power here, and then you need to turn this into, for example, standard normal type integral. So this would be a quadratic expression in the power of exponential. Then you know how to deal with it actually. Okay, so this integral, once solved, okay, is going to give you this. So it's going to be e to the 1/2 of the integral from 0 to t, or maybe the h norm of this is fine actually. Also, but you can also, okay, but you can also deduce it from, what do you call, moment generating function, isn't it? So why well? So what was the moment generating function? So if you have a normally distributed random variable with mu and sigma, then expectation of e to the tx is what? So e to the mu t plus sigma square over 2 t square. So you have it, right? So the mu is 0, so this term will go away. And if you substitute t equal to 1, so you're going to have what? Sigma square over 2 times 1 actually. So you're really going to get this expression. समझ आ रही है ना? ठीक है? So more explicitly I can say the exponential of expectation of 0 to t h of s dw of s is going to be equal to e to the 1/2 of 0 to t and h square of s ds, right? So this would be, I just wrote it explicitly. This is going to be the this yt. So the yt is what? Normalizing by the expectation. So 0 to t h of s dw of s divided by the expectation of e 0 to t, okay, h of s and dw of s, right? Just divided by the expectation. So it's really normalizing, but not normalizing in that manner that I just said. So you took the random variable and just dividing it by its expectation. So what would be yt then? So the yt is going to be this interesting process actually. What process? This process. E to the, so I know this expression, but this is equal to this. So I can write this as e to the minus 1/2 0 to t h square of s ds plus 0 0 to t h of s dw of s, right? Now, I have this process yt, but let's look this yt from another perspective, okay? And I think I discussed this example again. So, let's give this guy a name. So, let's call this process as xt. So, let's take xt as minus 1/2 0 to t h square of s ds plus 0 to t h of s and dw of s. Okay? And let's apply the Ito lemma on e to the xt. Okay? E to the xt. In other words, I'm saying let's compute dyt through Ito lemma. So when you're going to get this, what you will get? So your function is going to be simply e to the x. Okay? So you want to apply Ito lemma on this. So your function is going to be e to the x. So the derivative with respect to t is 0. Okay? Plus mu. So what is mu? Okay, so for that you can also write this in differential form. So the dxt is going to be minus h square of t over 2 dt plus h of t dwt, right? So the mu, in other words, your drift is this function minus h square over 2, okay, times the derivative of it. So it's going to be h square over t, so e to the xt. Okay? Or if you wish, you can write yt again. Plus sigma square by 2. So it's going to be h square by 2 again, right? Of t. And the second order derivative of e to the x. So it is going to be e to the xt and then equal to what? Yt and dt. Plus, so I'm applying Ito lemma. Plus sigma. So the sigma is h of t, right? It's going to be h of t times partial x by partial t, so it's going to be yt, okay, times dw. Is it making sense? So I can see that the drift goes away. The drift goes away. So here is another way to write y of t. So the y of t has this form, but y of t also has another form, and that another form is going to reveal something interesting about y of t. Okay? So what would be y of t? So the y of t is going to be, so if I write it in integral form, so it's going to be
e to the
what?
power h of s.
So it's going to be 1, if you're starting for example from 0, so it's going to be 1 plus integral from 0 to s, 0 to t h of s, and I have y of s, y of t. So the y of t is this guy. No, y of t is e to this guy. Okay, so I can write this as e to minus 1/2 h square of s ds plus 0 to t h of s dws, and let's not use the s here. If I'm okay, so I have e to the xt. So
Why not?
One consider h of s, and I have yt here, and yt is e to the xt, and xt is this guy. So I'm going to have e to the xt, and xt can be written as minus 1/2 0 to, for example, s now. Okay, because you want this expression to be a function of s. 0 to s, and h is square of some other variable, say, what should I do? U, du plus 0 to s, and h of u, dw u. So this is my y of t and dws. Okay. So here is what do you call the gain of creating all this mess actually. Why we did all this stuff. So what we did, we started with a deterministic process. We identified that it's normally distributed. We computed its expectation, exponential of the expectation, which turned out to be e to the h2 norm, 2 norm of h. And then, yt, then I defined yt as the e, so the stochastic integral divided by its expectation actually, which turns out to be this guy. And next, then I'm saying that there is another way to look at this process actually. And this process is that, treat this as a fundamental process, in other words, treat this as an Ito process, and then apply the Ito lemma on this expression actually. And when we applied the Ito lemma on this expression, we reached here. Okay, we reached here. And what does this is representing? So I have a sum constant plus a martingale. So this yt, which is an exponential process, is a martingale. At least in the case when h is a deterministic. Okay. So this yt is a martingale. What we are going to, say in fact, is that if, and I'm not going to prove it. So if you take h from L2 AD, okay, you can prove a similar kind of an expression for yt. And it turns out that yt would be a martingale as well actually. So if you take h from L2 AD, you can also take h from calligraphic L2 AD, and by applying the Ito lemma can reach to a similar kind of an expression, but for that case the yt is going to be a local martingale, not a martingale actually. Okay? Now I would like to throw a definition. Okay? So I'm just finishing and maybe then we can go to break. So here's a definition. This process yt, for a given h, this process yt of this form, we're going to call this process as an exponential, process actually. This exponential process is going to be pivotal actually in the Girsanov theorem. Okay. Here's a definition of exponential process. It's here. Definition. So definition is this. For h in calligraphic L2AD, okay, for in stochastic process h in calligraphic L2AD, this process, that is e to the minus 1/2 0 to t h square of s ds plus h of s dw as this exponential process actually, that is purely defined by picking a function from L to AD. I'm going to call this exponential process, or I'm going to give this process a name, xi h of t actually. Okay, so what was my yt, now I'm giving it a kind of an exponential process depending on h, or defined through h actually. Okay, so that's an exponential process defined through h. So for h in L2 AB at least, or maybe 0 to t at least, okay, we showed that exponential process satisfies this stochastic differential equation. Exponential h of t is going to be 1 plus. So if I rewrite the last expression that I have written, I can rewrite this as 0 to t h of s exponential process and dws, and this will satisfy this definition. Okay, and what does this show? That this is a martingale. So what would be the dynamics of exponential process? Okay, so the dynamics of exponential process are going to be h of t exponential process of t dwt, right? So I just wrote this integral in differential form. Okay. Here's the theorem. I'm going to prove it, just mentioning it, and you can see the proof. It's a readable proof, not difficult. So if you take h from calligraphic L to AD, such that it should satisfy this condition, that the expectation of exponential of h of t is 1, or this condition, or another condition which is called the Novikov condition, that the expectation of e to the 0 to t h square of 1/2 as well, h square of t dt is finite. So I have an h that satisfies this condition or this condition, then satisfies one of the condition, then this exponential process t bigger than or equal to 0 is a martingale. It's a martingale. Okay? It's a martingale. I mean, if you see my previous calculation, in my previous calculation I have already shown that for h in L2AB, simple, when it is deterministic, it's a martingale. Okay, but this is true more general than that actually. Okay? So out of all this discussion, so what is the key thing that we have to keep in our head? So the key thing that we have to keep in our head is that I can take an L2AD process and I can define an exponential process through it, and that exponential process is going to be a martingale if it satisfies one of the conditions. This condition is stronger actually. I mean, if this is, okay, so this condition is more stronger, right? This is weak actually. Okay, it's difficult to verify, while this is very easy to verify. For example, if you take a deterministic function, so take h to be deterministic, so this is by default true. Why? Because this is finite, this is h2 now. So if this is finite, then e to the finite number is a finite number actually. So the expectation of a finite number is a finite number. So this condition is by default true actually. Okay? So it's easily verifiable. So if this condition is satisfied, then your exponential process would be a martingale. Okay? This condition has a specific name. This is called the Novikov condition. Novikov's condition. Okay. So if H from L to AD satisfies the Novikov condition, or this expectation condition, then exponential process defined through it is a martingale. ठीक है भाई? If you wish, you can go through the proof of it. It's really a simple application of definition of conditional expectation and
सर जो ये सेकंड कंडीशन है
जी
वो एक बार फिर से आप बताना क्योंकि ये बहुत ऑब्वियस ट्रिवियल लग रही है
second one.
हाँ
नहीं, it's trivial when H is from okay, so H is from it's deterministic actually. But if H is from L to AD, then it would be a bit trickier. Why? Okay, for L to AD, I know that this is finite. So the expectation of square of the integral is finite. I mean, if you apply Fubini theorem, for example, so you get really the condition for a process to be in L to AD. But is it necessary that if a random variable is has an expectation finite, that exponential should have a finite limit? I think it's too much to assume. Okay, it's too much to assume. So this is not that trivial actually. This is not that trivial. ब्रेक करें 15 मिनट, सिर्फ 15 मिनट, उससे ज़्यादा नहीं, ठीक है? फिर आधा घंटा और करते हैं आपके साथ। हम जो है